Thank you. It's a real pleasure for me to be here and talking about something which actually we started with Chetan a few years back, and at the beginning I was kind of meh about this, and these were really the guys who sort of took the idea very seriously. I would say that they had the right instinct about the problem, because I think there are still we're trying to do some calculations. We have been doing some calculations, and there are some interesting answers that we get in a framework which has a lot of problems, and there are lots of questions you can ask about whether it makes any sense at all. But the fact that it gives us interesting answers, I think, is well, motivation enough, at least for me. So what I will try to talk about today is one part of it that I have been working on with several people here who I have listed, and also work in progress. And I will try to mainly focus on that, but I'll spend some time on the background. And I'm afraid maybe many of you have heard some version of this talk somewhere. I'm quite sure. So if you feel like, you can sit back, relax, and enjoy the ride. Also, it's late in the day, so I promise I won't keep you long. So this is the title, Blackish Holes, and I'm not sure about you, but I get kind of excited about these numbers and these pictures. I'm a bit simple-minded that way, but I think it's a pretty amazing thing. If you just look at naively this number that people can now access experimentally, it's 10 to the minus 24 meters. It's quite unthinkable. Of course, it's very, very far away from what we would perhaps like to know if we want to understand quantum gravity, and in particular perhaps quantum aspects of black hole. That's still at least 10 orders of magnitude higher. But okay, I mean, what we have now is also quite impressive. But the fact that we have this now raises many questions. Is that, well, one immediate reaction of this, once you see this, is that, well, hurrah, we have seen black holes. And then immediately you can ask, have we really? Because there are several questions you can ask. One is that even if it is a black hole, well, can we ask what are the quantum properties of it now that we have a picture of it? And what tells me, suppose I'm a very crazy person, and I mean these ideas have been around for a very, very long time. I mean, what is there in principle in physics that tells me that it cannot be an extremely compact object and it has to be a black hole? This cannot really be ruled out by an observation, or I mean, if it has to be ruled out theoretically, there are certain assumptions, at least I think we have to make. But those are questions you can certainly ask. And in particular, for example, there's a very serious group of people, I think, in the world now who are trying to sort of analyze what could the phenomenology be if this were not a black hole but a black hole mimicker. So that's sort of a motivational picture, you might say. So now, with that picture and with those questions, let me get straight to sort of the high energy theoretical perspective on it. So we of course know at least there are two major schools of thought, which say, one says that, well, event horizon is a perfectly smooth and nice place, and if you want to understand quantum aspects of black holes, one way to do that is do the standard Euclidean quantum gravity that Gibbons-Hawking did, and its various generalizations and embellishments. If you do that, then what I think one remarkable lesson here is that, or at least realization here, is that if you do Euclidean quantum gravity, somehow the Euclidean description knows about the UV physics, but it is unclear to what extent it knows, and whether this knowledge is systematic or just accidental. Of course, there is another school of thought which says that there is a structure at the horizon scale, and this is a school of thought where people try to build the microstates given a particular black hole, or conserved charges of a black hole, using some UV complete description like string theory, or its low energy descriptions, and so on and so forth. So of course, I should also say that there are many other thoughts, including trying to you can also come up with proposals, I think that's a fair word, where you actually modify quantum mechanics in a way that there is no such firewall or fuzzball and so on. And I don't personally like to put people in boxes, but anyways, this is I think a natural way of classifying it, classifying activities that people are trying to explore, at least some of them. So what I will try to do or describe is actually none of this. What I will do is an extremely ad hoc, extremely baby version of something, and the bottom line is that is the following: that whatever I do, if you allow me to do that, the answers I will get or we get is I think interesting to think about. That's the selling point. So this is roughly speaking the picture. So I started with the picture of this event horizon telescope. Now you might say, well, this is kind of a hopeless question to ask, because if you want to ask questions about what are the quantum properties of black holes, well, 10 to the minus 35, that's ridiculous, we are never going there. But if you go back in history, it's also true that we did not have to probe at the level of atoms to know about the existence of atoms. You could do that by looking at mesoscopic observables and mesoscopic physics, just by looking at Brownian motion. So it's not true that if I want to know physics at a certain scale, I really have to always probe it at that small scale. It could also show up at a slightly bigger scale, or a mesoscopic scale, so to speak. So that's a hope. And in fact, as I said, that there are very nice ideas laid out by these gentlemen in a review slash I guess review an Outlook paper they wrote, which I encourage you to read. It's very, very nicely written. Anyway, so the picture that I want to have in mind is the following. So suppose there's a black hole here, which is denoted by the black circle or filled up circle. And for some reason, because I want to have a nice asymptotics where I can do things, I want to put it in a box, which is why I'll put it in an asymptotically ADS box. And for some reason, this is the ad hoc element of it. For some reason, I'll just imagine that there's a wall just outside of the black hole, and whatever field propagates inside this geometry has a Dirichlet boundary condition. So this wall is a completely ad hoc and non-dynamical in this description. So if you remove the wall, the rest of the geometry, of course, solves Einstein's equation. So there's a semi-classical or actually classical geometric description of it. But if you include the wall, at least it's not easy to come up with one, and there may not even exist one. So this is an idea that goes back all the way to Thuft a long time back, and later on Israel and Mukoyama, which also mentioned and to some extent discussed in the last talk. And morally speaking, I think what I'm doing has certain semblance to what Debojyoti was doing also, but I guess in a slightly different way. So yes.
Do you have in mind this wall around the event horizon or the local apparent horizon?
This is just the event horizon. So for me, yeah.
I see, but that could be, that in a sense is determined by everything that happens much later. So this would be some very non-local.
That is correct.
Change of the theory.
That is correct. Which is why I do not know. Whether there is a low energy effective field theory description or effective gravity description that will actually successfully describe this. Yes. Yeah.
I think low energy effective field we don't expect to succeed. It can be a proxy for some UV completely.
That's what I would also say, but yeah, I agree with that.
The thing is fine, but it has to be totally acausal. The event horizon is determined by what happens 100 light years after, but today you say there's something special.
But you could also use the same argument for BPS black microstates, right? So as an existence proof, we already have such solutions.
What's the acausality in the BPS microstates? There is none that I know of. What's the?
No, but
this is a completely
at the horizon it stops, right? Before the horizon it stops. This is an ad hoc way of capturing that.
But I'm saying you will have to violate causality. Today, I don't know where the event horizon will be. That is dependent on the entire future history of the evolution.
So if you're talking, but we are not talking about that even in the BPS black hole, right? So if you have a Schwarzschild solution, it's just a solution that is given to you. Or if you have a BPS black hole, it's a solution that is given to you. So you could construct, and that we have microstates. So I'm not saying that, if you want to construct the dynamical evolution to the horizon, I agree with you. But if you take this as a, given object, then you could, of course,
Given object, you need the entire history from
So,
now till
so,
later.
so, Sandeep, I think
Sorry.
I think
This is
we
complete violation
we
of causality.
we do not. I think it's fair to say we do not know how to form this from a collapse. That's for sure.
It's more serious than that. In no causal way would you know where to locate this surface today.
No, I would not. I would not. But yes, so
You depart from causality in
yes, I agree. I agree.
Fine, that's all I want to say. I don't know.
Yes.
Low energy effective filtering at all.
It's not. It's a violation of causality. Causality is the most.
You can
sacred
think of it
thing.
as a regulator if you like.
No,
So if it is a, if it is
I'll contest all of those facts. It is a violation of causality.
I agree with you.
Okay.
The way you was yes. I mean yes, I agree. So good. Okay. All right. So the question that you can ask, nonetheless, is why? Well, are there examples, for example, where there are, one can cook up or come up with yes.
I won't say more.
so
Go ahead.
do you think that cutoffs in quantum filtering violate unitarity?
Okay, causality is the fact that I can't determine today.
Yes, I think the answer is yes. If you have cutoffs,
Yeah.
for example, if you have a contact term like the Fermi theory,
Yeah.
that's something with the cutoff. You won't excite the mediator.
Yeah. So it will violate unitarity.
Yeah.
That's
Yes.
exactly my point. So this will violate causality, but what we are really trying to compute, that's precisely the sense in which I was saying that it is a regulator. So you would get low energy effective filtering if you can reproduce from this. This is a good regulator for causality, unitarity, whatever else things that you're breaking.
I don't want to get into cutoff because string theory is a UV finite theory and it preserves causality.
I agree with you.
Okay, it preserves causality.
I agree with
you. are violating causality.
I am
That's
right.
all.
Yes.
I am violating causality in the UV. I do not know what the UV is. That's all.
Arnab has to
But
violate causality
Fran-
20 in time.
I think there will be a bigger causality violation. No, but I mean yes. I mean, if I could, for example, give you a calculation where I could form this from an initial collapse, I would have a precise answer to this. But that I don't think it's possible to do also here. But in spirit, I think it's what Chetan is saying. When we put a quantum field theory on a lattice, we break a lot of things. Okay, good. So the point is that right. You can ask, are there boundary conditions that can give you certain interesting physics that we know and love from black holes, like thermalization, decoherence, maximal chaos, and so on and so forth? Maybe I should speed up through this. And the short answer of this is yes. And you can, for example, well, there are many examples. One could be closer to us. That is essentially if you do a quench with a boundary state, you start from a boundary state in a CFT, you see that it thermalizes and so on and so forth. Essentially happens because of the boundary state, boundary condition that you started with. It's in that sense, boundary conditions can certainly affect these physics quite a bit. In fact, realize them. All right. So with that motivation, this slide is not really needed, but I'll just mention a couple of lines. One is that the kind of questions in some sense that we are interested in, at least at the initial stages we were interested in, had to do with real-time dynamics, like for example computing spectral form factor and so on and so forth. So the idea is that if you have a quantum system, nothing to do with black holes, just take any quantum system you like, you study the quantum system at an arbitrarily long time scale, then you automatically know about arbitrarily fine UV data of that quantum system. And the same statement holds for black holes. And this statement, by the way, that long time dynamics is essentially coupled to UV data is not new. It's known to physicists for a long time. In particular, for example, people study spectral form factor, which is what I wanted to introduce here. It's essentially this object. You take a partition function, standard partition function, except you take your inverse temperature and complexify it. And what it does is that, and take a mod square, of course, just to make it real. And what it does, of course, you immediately observe that it knows about the finest gap in your spectrum. And essentially, if you look at this, if you study this particular observable, you will see certain features which will know about the finer details of your the quantum system that you have in your that you want to study, including black holes. And this slide was just to mention that there's a nice way of understanding realizing spectral form factor in terms of what people sometimes call return probability. If you start from a thermophile double state, it's basically the return probability of the state, return probability of the fact that the state comes back to itself. Anyway, good. So let me just chalk out the calculation very quickly. So let's start with the BTZ geometry. In fact, it's not needed to stick to 3 dimensions, but for a lot of reasons this is particularly useful, extremely convenient. Take a probe scalar in it. That's also nothing new. We do that all the time. And then write down the equations of motion with the standard separation of variable and so on. So what you get is basically a radial Klein-Gordon equation with some potential, and then you solve that. And one reason you start in 3 dimension is because you can solve the radial equation exactly in terms of known special functions, in this case hypergeometrics and so on. So nothing new so far. Usually what we do is we say that if we have a black hole, we say that okay, at the horizon we are going to impose ingoing boundary condition. That's the usual stuff. But now for some reason let's do this ad hoc thing and say that I'm going to impose a Dirichlet boundary condition on this field at this wall, at the location of this wall. You can actually replace the entire wall by just this boundary condition as well. So R0 is the location of the wall. So what happens as a consequence of this is that you get a bunch of spectrum, not a bunch of, you get a quantum spectrum which is labeled by essentially 2 quantum numbers. One is the angular momentum, because we started with a BTZ which had an angular direction. That's the angular momentum part, which I denote by J, and later on I think I'll also use M. Sorry about that. And then there is another another quantum number, which is this N. Okay. So this is a fairly simple and straightforward thing that you can calculate. Unfortunately, this is a spectrum that cannot be exactly analytically computed, but somewhat semi-analytically you can do things. For example, you can recast the Klein-Gordon equation that I flashed in the last slide in terms of essentially an effective Schrodinger equation with the potential. And the reason you do, the advantage of doing that is that now you can use WKB as long as WKB approximation is valid, and you write on the nose, you basically, there are certain WKB connection formula and so on. It's fairly standard. What you get is a quantization condition that you can then solve. Of course, this also has to be solved numerically if you want to know the full spectrum for arbitrary ranges of parameters, but there is a certain range when this epsilon is essentially the location of the wall, the distance between the wall and the horizon. If you take that location to be 0, in other words, if you take the wall very close to the horizon, then there's an analytic formula that you can write down, or you could also take the full numerical solution and do a fit, which I think Chetan also did with friends and so on. You get some expressions which are useful. Good. So now with this, if you decide to now compute, because you have the spectrum, of course it's numeric, so you have to do a numerical sum and so on. You cannot just do an infinite sum as it is, but nonetheless you can do this and you can make sure that your calculations are numerically stable and so on and so forth. You compute your spectral form factor, and what you find is this picture. Now, why is this picture important or interesting? This picture is interesting for the following reason. So whatever this. So first of all, this axis are in log. These axes are log. So this is a log plot. It starts from 1. That's just a normalization, and now it decreases. That's not surprising. It happens for every system. But at some point of time, this curve bends upwards and then it plateaus. So this is essentially known as deep ramp and plateau, very well known now. But the significance of this is the following: that if you see a ramp, generally speaking, thumb rule essentially is that if you see a ramp in a similar study of a quantum system, and if the slope of the ramp in the log plot is very close to 1, you would be tempted to think that this is like a random matrix theory. At the very least, there is certainly a level correlation or a level repulsion. More technically, sometimes people use the word spectral rigidity. Even if it is not random matrix, there is spectral rigidity. So the point is, I just want to re-emphasize, I guess, that this is a free theory that we are studying. And the fact that there is such a spectral rigidity, which is somewhat close to a random matrix theory answer in terms of the slope of the ramp, is kind of interesting. And this happens when you take the brick wall or this Dirichlet wall close enough to the horizon. If you take it farther away, this actually goes away, and in fact at some point it looks like a harmonic oscillator, where basically what happens is that there are just regular oscillations. So if you plot the same thing for a harmonic oscillator, there are no ramp anywhere, it's just simply oscillating after this dip. So that's a very nice and very intriguing observation, because for a free theory, actually I don't think we were expecting to see something as neat as this, but it happens. And
What decides how close you have to?
well, it's a transition. Sorry, it's not a transition. It's a crossover. So there is no scale. If you are asking what decides, or yeah. So, but if you are asking, does it happen exactly at a sharp point, or it slowly becomes this? This I do not think I can answer reliably, because this, for that one has to generate many such data, and it's a bit difficult to say whether it is happening very sharply or very slowly. That I don't think is very clear. Most likely it is happening very slowly. I mean, it's not happening just at one point.
Same calculation in a Rindler background.
Yes, same answer. Same answer.
You see these things.
Exactly same answer. Yes, and that's going to be well, I would not mention it, but that's yes. I'm glad you brought it up, because then actually the claim is the following, that all I need for, so you can ask, what do I need for this? The thing that you need for this is a local Rindler structure, and the following thing, you need to have an angular direction. So the reason for the angular direction is the following. If you look at the spectrum, the behavior of the spectrum, here I have plotted one. So this one is this n quantum number, if you remember. So this is how the spectrum behaves as a function of the angular momentum. And you see that the curve, the behavior has a certain curvature towards it. It's not linear. In harmonic oscillator, the spectrum is linear, right? This is certainly not linear. In fact, it looks almost like a log. But anyway, you can do a log fit if you want with certain twists and turns. But the point is that it is essentially this curvature of this graph or this plot or this curve that is essentially responsible for this. So to again summarize, what do I need for this ramp to exist is a Rindler redshift and angular momentum. Without that, I will not have the ramp. Okay.
The total time scale is governed by the surface gravity of that horizon.
Which time scale?
For the rise, or is it much longer?
Yes, no, it is. So it is, that is in turn given by where I'm placing the Dirichlet. Yes.
The two are sort of connected.
The two are exactly. That gives exactly this time. This time scale is exactly that. Because if I do not impose this reflecting boundary condition, maybe I should mention this. So you might wonder what happens if I just use the standard ingoing boundary condition. What will happen there is that this dip will keep continuing forever, because things are just going in. It's never coming out. So it will always keep decaying forever. So at the point where you change the boundary condition, this curve also changes. It's essentially captured by the same scale. It's there by essentially by design. What is not there perhaps by design is the fact that this has to rise in this manner. Okay. How am I doing on time? It's okay. 20 minutes? All right. Good. So the key aspects are the following. Let me try to summarize. So as I said, there's a non-trivial level correlation that gives an RMT-like ramp, but it's not RMT. I want to emphasize that as well, because you can look at, for example, much finer things like the level spacing distribution, and it's not Wigner-Dyson, but okay. And as I said, we do not have a theorem, but there are strong circumstantial evidence for the three things to be there when such a feature will emerge. One is the reflecting boundary condition at the wall. You want to have a non-vanishing angular momenta and a local Rindler structure, which is to say that you have to have enough redshift. This is just a side remark that there are several different works. I would only quote recent ones from various different points of view, and people are trying to calculate different things completely unrelated to what we are doing, and also perhaps not aware of us, but which has very similar flavor in the sense that, well, let me just mention maybe one. You could ask, for example, if I want to reproduce the Hartle-Hawking calculation that black hole has an area, worth, entropy, and so on. How can I do that? Can I do that without? Sorry, I don't want to say wrong things. Okay, let me make the right statement. So what these guys argued is that you can show that the Hartle-Hawking vacuum can be approximated by essentially a brick wall like vacuum if you insert a right kind of defect operator. So that qualitatively is very similar to inserting essentially a Dirichlet wall, cutting the horizon off and putting certain operator on it. But as I said, this is not exactly what we are doing. So there are differences too. I just want to say that there are similarities in thought. And there are other works also. Of course, Chetan here has also done entropy matching calculations and so on. Good. So now let me ask a different question. So that was much more complicated stuff in some sense, that spectral form factor, you know the dynamics up to an arbitrarily long time scale and so on. But let's ask a very simple trivial question, which is, can I extract? I mean, it seems like in this system, I will always have normal modes, right? Because I have imposed a reflecting boundary condition, I will always get normal modes. But we know and love the black hole quasi-normal modes. We certainly want to have that. And that in a certain, that's I guess in some sense also observed. So is there a way to extract the black hole quasi-normal modes within this framework? That's a reasonable question. So to do that, let's first compute, let's now use ADS-CFT. Now I can use my ADS-CFT dictionary to compute a correlation function. You could do that. I mean, this is actually if you do not have a boundary, this becomes a bit difficult to define, but you can always compute a bulk 2-point function. That you can always do. But suppose you compute that, then the poles of this Green's function is going to give you essentially the modes that I just showed you. So if I choose a particular location or the distance of the brick wall from the horizon, you get a particular set of modes, which one of them is shown on the left plot. And on the right, what happens is if you decrease the distance, the poles somehow become denser. This is essentially what happens, correct? So these are discrete quantized poles that we have already seen, and the only observation from here is that the brick wall, bringing the brick wall closer to the horizon, increases their density. Great. Can we study how their density increases? The answer is yes, of course, because we know the answer. We have the, you can do it two ways. You have the full numerical data. You just say that, okay, suppose I fix my energy to be 10 in some units, and I keep changing my epsilon parameter. How many states do I find? And what you can do, because there are two quantum numbers, you can fix one of them, just vary the other and count. So if you, for example, on the left hand side, this is the counting, this is a measure of the counting. So here I have fixed the angular momenta and I'm counting up to a certain energy how many states there are as a function of epsilon. So as epsilon decreases, you see that this function grows logarithmically. This is a logarithmic behavior. The blue dots are the actual numerical data and the red curve is the fit, if you wish. On the other hand, if you fix the n quantum number and vary angular momenta, you can ask the same thing. I want to just count how many states there are. And there is also an increasing curve. And the blue ones again, blue dots are again the numerical data, and the red one is the fitted curve. It goes as epsilon raised to -12. Clearly, between these two, there is a scale separation for sure, because epsilon is appearing in two different ways. In fact, it's not surprising, but So yes, so let me keep that. Let me keep it. Keep a note of this for the time being. Great. So the conclusion is that no matter what I do, if I decrease epsilon, number of states that I find are increasing very, very rapidly. Excellent. So now, given a cutoff, what I can do is I can write down my Green's function, my 2-point function in the frequency space in terms of using standard contour identities and so on, in terms of residues and sum over discrete residues. These residues are essentially, these omega i's are essentially the real the frequencies or the modes. But the moment you find that there are too many of them, you could say, well, this discrete sum can be approximated by a continuous integral, where this rho is nothing but the spectral function, right? Yes.
Modes don't have an imaginary part.
No. These are all, because it's a particle in a box.
Yeah, that's what I'm saying.
Exactly.
Because the black hole quasi-normal modes are.
Yes, yes. That's what I want to see, how it comes out, or if it comes out at all or not.
But is it outgoing at infinite?
It is outgoing. Yeah. So at the horizon, yeah, exactly. I mean, I have kept both ingoing and outgoing at equal strength, precisely. In fact, it's a good question. I mean, it's an interesting question, because you could ask the following thing, that can I somehow engineer this, that most of it is ingoing but some of it is out? Can I have that parameter? That's an interesting thing, which, yeah, I don't have a precise answer, but I think that's an interesting question to play with that. Okay. So nonetheless, so let's do this. So you could say that, well, I mean, the poles are, they have accumulated so much, so densely, that I can no longer, distinguish two poles. I am a finite observer, I have finite energy capacity or budget. So I'll declare that it's a branch cut, which is when you replace it by a spectral function. And of course, when you do that, then what you get is the following. You get, from this relation, you essentially get this left blue circle or whatever, ellipse. This is essentially an identity. It follows from the definition of the Green's function here. But if you use the Green's function and the poles that I showed you that we have in this problem, compute its residues, what you find is that this object coincides with what I call imaginary part of GBH. And what is this? Imaginary part of GBH is essentially the Green's function that you would get if you imposed purely ingoing boundary condition on the scalar field. Yes?
Sorry, just a quick question. So where is the information of this location of the weak one here?
So that is in this twiddle. So when I'm going from this line to the integral, I'm ignoring certain things, right? There are certainly errors. So the error terms will know about where I have placed my wall.
To zero, you get back.
Precisely. So another way of saying it is that this is never really the correct answer, as long as I can resolve it. So no matter how dense you populate, if I can look very closely, I know that there are corrections and it's actually a sum. I'll never see this. That's a correct statement.
Interpret this as how to recover black hole from weak one.
Yes. Yes. That's correct. So right. So I think what is really interesting is that the left, as I said, the left blue ellipse is not, I mean, that's an identity, but the fact that if you take this formula and just evaluate it for this problem, what you get is the imaginary part of the Green's function of the black hole that you would have gotten if you imposed purely ingoing boundary condition to begin with. And now we know that the poles of this object are the quasi-normal modes. So given this model, if we just do this, the jump discontinuity knows about the quasi-normal modes. So if you like, this is a way of extracting out the black hole quasi-normal modes from this brick wall model. Okay.
Simple explanation why there is a minus sign.
No, unfortunately, I do not have one. Yes, I have been asked this before, but no, sorry. Good. So, right. So you can ask, what do these quasi-normal modes, I mean, what is this emergence based on? And it's fairly clear what this emergence is based on. First, you need a parameter to tune these gaps. This is a gap spectrum, of course. It's a finite entropy system. But if you have a parameter to tune this gap, then at some point you can declare my observer doesn't know how to resolve, and then it's a continuum. That's an important thing, but that's not enough. You could do that for any system. You would not get black hole quasi-normal modes. What is important is what the residues are at around these poles. So this is the part I find kind of intriguing. I do not claim that I have understood it completely, but nonetheless, that's the observation. Now, what I want to say is also the following, that note that this brick wall is endowed with a Dirichlet boundary condition always. In other words, why am I making this statement? I'm making this statement because there are many reasons behind trying to impose certain cutoffs or regulators like these brick walls. But in many such cases, what people do is that they use what is called a shrinkable boundary condition. Meaning, suppose we had a boundary condition on the wall which varied as I take the wall closer and closer to the horizon. And exactly on the horizon, it becomes, suppose, purely ingoing. Then it's a shrinkable boundary condition in the sense that it goes back to what we are used to. So this is something that people do, and what we are doing here is certainly not that. But there's an interesting reach story, even with the shrinkable boundary conditions that you can work out in gauge theories and so on and so forth, which I myself do not know very well, but I think it's very intriguing. So I'm very tempted to learn these things, and there are edge modes which cause entanglement and so on, which will I feel like they will have a story here to tell also. Anyway, I don't have any precise things to say. Yes.
So it's not, yours is not this, because as the distance goes to the cap closes, you still have reached level boundary condition.
Correct. So it's not irregular.
Yeah.
Just a remedial question. I'm very sorry. I understand why you get the branch cut, but why do you get imaginary paths, of the right sign in the modes? Because the damping in the quasi-normal modes that you see at LIGO,
Yes.
because they are imaginary paths.
That's correct.
Right? And why are you getting that imaginary path? Am I missing something? I'm so sorry.
Well, I don't know. What I'm saying is that if you just compute this jump function is just a function. Right? Nothing.
Jump from that into
It's just this. it depends on what the residues are and so on and so forth. They're just some functions. And in this case, in the case when you have a Rindler horizon, you will see this. Why? I do not know. This is not something I have an understanding at a deeper level. Yes.
Just this blue part,
Yeah.
why does it showing that all the quasi-normal mode spectrum is there? Just the fact that in is pi omega.
The blue part? No, the blue part you can ignore. All I'm saying is that if you just look at the spectral function, it will already give you all the quasi-normal modes. The blue part is just telling you that it's nothing but the retarded correlator. So if you like, the retarded correlator has that information. Right.
the ingoing is crucial for the negative,
Yes.
the imaginary part to have the right sign.
Exactly.
Because it damps, because it goes in.
Exactly.
And I'm wondering how you're getting the damping.
I don't know. Somewhere the symmetry is broken.
It's bizarre to me how you're breaking that
I
time.
think it's outgoing at infinity, maybe that is true. Strictly outgoing at
Is that right?
I'm not sure. At the horizon, I have both here.
Yeah, that's
So
but at infinity has reached my boundary. Okay.
yes,
Then I don't understand.
I do not know.
Perhaps some analyticity property of the
I think in doing these manipulations, somewhere that symmetry is being broken.
I think that, so the way we did the calculation
Yeah.
in the paper that you mentioned earlier. So the way we did it is by looking at the correlation.
Right.
So the correlation function in the cutoff going to zero limit just transition to the Hartle-Hawking mode.
Right.
So there is I think this sort of a, so somehow you can the Hartle-Hawking correlator knows about
Exactly.
this quasi-normal mode. So but there this sort of a choice issue doesn't seem to appear somehow. I don't understand. I don't understand your calculation well enough to comment on the choice of the sign.
Yeah. What should I say? So for example, when you get a Hartle-Hawking correlator, right, it looks like a thermal correlator. Of course, by definition. But the system that you start with is not a thermal correlator. So there is a dissipation somehow in going to that limit. So it's the same question. How is this dissipation emerging? So it is in, I think I have my feeling is that it's in throwing away these correction terms which kills this dissipation. Which introduces this dissipation, but with the right sign. That
I'm saying that if you're starting with a general, high, let's say look at the high energy state.
Yes.
Like eigenstate thermalization type of thing.
Yes.
You look at some small operator correlator.
Right.
And if you're looking at it, somehow you're not surprised that the correlator is thermal, right? I think it is. That's not. I think it is the same. If I understood correctly, that's the same thing that's happening.
That's essentially the same thing that is happening. Yes.
So if that is the case, I think there is probably. This should arise just because of thermalization or something.
I guess. I guess yes. I would guess so, but
It sounds like that you're working just with the normal modes directly.
yeah.
In our case, for instance, we are actually looking at a state which is
Yes.
You're
computing the position space correlators.
Yeah. So
Right.
Yeah, we can talk.
Sure.
Sorry, what is
Yes.
DI?
Sorry. These i's are just integers because these are discrete sums. Sorry. These are labels. Right. Good. Yes. So for example, just one comment. So if you take this frequency space correlator and do a Fourier transformation, in the continuum limit, I'll get exactly the position space correlator that you have, for example. But if I include the corrections, of course, computing it is very hard, but it's clear that those are terms which will spoil it once it starts contributing. Okay. Good. Excellent. So now, how much time? Oh, almost over. But okay, let me take a couple of minutes and make a statement which well, I have made already, but it's kind of, once you make it, it's kind of trivial. There's a way of understanding or perhaps recasting where this separation of scale is coming from. If you look at the WKB wave function altogether. So what we have here is basically, remember the original problem you could recast in terms of a Schrodinger problem, and you could just look at, for example, the wave function. I have plotted here the second derivative of it. It's like the kinetic energy, if you wish. And here, you see, what I'm doing is I'm keeping this n fixed, but I'm studying how that object, this second derivative of the wave function, behaves as I increase the angular momentum. And as you can see, that there is a peak, but the peaks are not dramatically changing as you keep changing m. So there's an increase, but it's a slower increase. On the other hand, here when you keep the angular momentum fixed but increase n, the change is pretty dramatic, and in fact the reason I do not have higher values of n is because it becomes extremely sharply peaked very close to the brick wall. So what that means is that there are two kinds of localization or time scales in play. One is where the sort of localization is still somewhat spread out, and that spread out localization time you can measure just by simply estimating a light traversing time from a very close to the horizon place to, let's say, infinity, and that will scale as log of epsilon. On the other hand, the local time scale is just simply the local gravitational redshift. That's 1 over root gtt, and that's nothing but this epsilon raised to 1/2. So that, I think, has very nice and very clean scales arising. It's not a surprise, and it should happen for any kind of problem, whether you anyway, of this nature. And do I have 2 minutes or maybe? Oh, okay. So this is actually this is something you can play with. I would not mention much about this paper because I think it's a bit tautological. Am I being recorded? Oh, sorry. You could ask, for example, so the question is that let's forget about all of what we are talking about, but is there a sensible way in which, let's say, I start from an asymptotic data, in this case, because I'm in ADS, I set up something and I let it collapse, and it collapses and makes what we are discussing? The answer quite clearly is no, right? In classical gravity, it will go close to the horizon and keep collapsing. You cannot stop it. But nevertheless, let's do it. So what you can do is this is the generic ansatz of a geometry, and you can try to glue, for example, something like a collapsing shell. So where outside the shell you have a BTZ, inside the shell you have ADS. And so that's these choices of these f functions are corresponding to those two. R equal to Rs is the location of the shell, and you imagine that now there is a scalar field which is hovering around, like the probe one that we had. So let it evolve. This is like a global quench in the CFT. If we let it evolve and you use the standard junction conditions, what you find is the following. You have the Israel junction condition for geometry, and then also for the scalars you will have some junction condition where an expression like this essentially appears, or you can massage it in so that it looks like this. Now the interesting bit is the following. If you take the shell to be very close to the horizon, then your f1 is 0. Is that right? No, sorry, I said the wrong. f2 is 0. f2 is this one, right? So if r is very close to rh, that drops out. So the only term you are left with is essentially this term, and that term is a product of two terms. One is phi 2 plus. Phi 2 plus is basically the scalar field inside the shell, which is regular at the origin. Excuse me. Phi 2 plus is the scalar field outside the shell, which is normalizable at the boundary, and then del r phi 1, where phi 1 is the field inside the shell. Now from this, so this product has to be 0. So you could conclude that classically there is certainly a Dirichlet boundary condition on the field that phi 2 plus equal to 0 emerges if you consider this. It doesn't say why it should stop there, but all it says is that if something happens at the horizon scale, then it's not crazy to impose phi 2 plus is equal to 0. But of course there is the other one, but that is for the field within the shell. Suppose we do not care about what is happening within, then this is a natural thing to do. Okay, good. So I think I have used up most of my time and most of your patience. So let me just summarize. There's a huge list of whatabouts, which I think is quite formidable. And I'm not sure that I will say that this is the way one should think about things, but I'm certainly intrigued, at least personally, that this model, this crude model, gives so much. That I think is a very intriguing thing, at least for me. And there are certain follow-ups, etc., etc. There's some work that well, Diptarko and I are doing for a while, and in some sense, since he's here, this is kind of a passive-aggressive remark, but hopefully that is okay. Anyway, there are other fun things, but I'll end with this. That I like this particular quotation, or these are my principles. If you don't like them, I have others. Trust me. So one thing I honestly think is also quite interesting, is quite far from what I have been discussing, but not far technically, is that you could actually do a lot of these calculations, putting it on a lattice, and that lattice would have to be defined on a hyperbolic geometry, and that can be done. And there are some fun things that happen. So perhaps some other time I'll be able to tell you. So thank you. Thanks for your patience.
It's quite late. Questions, pressing questions.
Yeah.
This the structure to the one function. So is that like a generic feature when you put a button?
No. It's when you say, so generically you just have poles. That's all. But it's the moment you say that, okay, my poles are very close to each other and I do not have the resolution, you replace that by a branch cut. That is where you're throwing out information by hand. You're saying that I do not know that these are poles. So the moment you say that, your poles become a branch cut.
Just by doing the integral,
Yes, in going from the sum to the integral. That's when you're throwing away the information that there is a gap. That's why you are getting dissipation. I mean, that's no wonder that dissipation will happen if I throw out information. Sure. But I think it's kind of interesting the way it happens.
So you don't get a discrete set of causes?
No, discrete, yes. So, sorry, I should, so this is, no. So what happens is the following. Yes. So what happens is the following. Initially, I just have normal modes, discrete set of normal modes. As long as I can resolve them, they remain discrete set of normal modes. The moment I say that I can no longer resolve them, they are all on the real axis, they become a branch cut. Now I compute the spectral function, which is basically a jump across the branch cut. That object is also a function of the frequency. That has discrete poles in the quasi-normal modes.
I think if you jump the other way, maybe you will get the other side.
I see, you're saying that will give you the advanced ones. Possible.
But the retarded Green's
Possible.
function, it is
Yeah,
not
that's,
very
yeah, I have not checked that. That's an, yeah. That's the only place it's breaking a direction. You're right. I think he's saying or suggesting that the jump has to be taken in one direction. I could also take it the other way. So maybe the other way it will give the advanced. Could be. This I have not checked.
But the retarded Green's function as such, without taking the imaginary part, is what has the poles, right? Like you just evaluate the retarded Green's function, and that has
Yes.
the quasi-normal mode.
Yes.
But here you're saying the imaginary.
Oh, sorry. No, sorry. Okay, ignore this. Look at this part. Maybe that's the better thing to do.
Yeah, that's why I've been always.
No, sorry. No, what I mean is that what you get here is exactly the Green's function which have poles at the quasi-normal modes, but the Green's function have been evaluated by imposing ingoing boundary condition at the horizon. That's what I meant. Yes.
Just say one last thing, then we'll chat later. If you're willing to give structure to your brick wall,
Yes.
and have stuff which can absorb things and all, then you're saying, then I would say you've got a hologram. N equals 4 is your brick wall, super n.
I mean,
Why do
you mean at the
insist-
boundary?
Yeah, because that's what holography is. As seen from outside, you have a boundary. It's called the n equals 4 super n.
Sure.
But if if you say you have no structure and you have just reflection, then that's like a dramatic thing to say.
Yes, of course. No, I'm not saying I know what mechanism gives rise to this. Absolutely not. I have no
You
clue,
see,
in
allow
fact.
for some structure, and then
Oh, yes.
and then how is it so different from saying replace the interior of a D3 brain geometry with a n equals 4 super Young-Mills theory?
No,
Okay. Same idea.
well, I mean, I mean, okay, so one thing that I can morally see that this is very close to is, of course, this stretched horizon discussion that people have been doing in the context of black hole for decades. There is probably a connection that one can make. Yes, certainly.
And all I'm saying is the stretched horizon precise version
Mm-hmm.
is what we call holography today.
Fair enough. But here, I have an asymptotic ADS boundary where there is already an n equal 4 super Young-Mills leaving. So, yes. No, I mean, yeah, I don't have anything precise to say about the nature of this wall or the stretched horizon.
One thing I will say is that even if you add structure, so the low point correlators are unaffected.
That is right.
I think that's why we view it as a UV regulator.
That is right.
What I'm saying is view it as a proper, hologram that you might get in situations.
That's
Oh,
where
ye-
the gem is coming from.
And then it's fine.
You are saying do more of it. Yes, I'm I'm up for it. You're saying do more of it. I agree.
I mean, that could make sense of the idea.